Jai Hind everyone. In this lecture of the subject electrical machines, I am going to discuss about the effect of variation of mechanical input and excitation on parallel connected alternators. This is a topic of synchronous machines. Here I am going to discuss the effect of variation in mechanical input on performance of two parallel connected alternators. This is the system. Let us consider that a common load is connected over here. A common load is connected over the system. This load is being supplied by two alternators, alternator 1 and alternator 2. Two alternators are being driven by two prime movers, prime mover 1 and prime mover 2. So, when two alternators running in parallel are loaded, the division of load between them is actually governed mainly by the speed load characteristic of the prime movers. As shown in the figure, the two alternators are being driven by prime mover 1 and prime mover 2. So, the load shared by two alternators would be dependent upon the speed load characteristic of the prime mover 1 and the prime mover 2. The speed load characteristic of two prime movers is shown in the figure. It is represented by the two solid lines, line 1 and the line 2. This is representing the total load shared by two alternators which are connected in parallel. We are assuming that load P is shared by alternator 1 and load P is shared by alternator 2. So, the two alternators sharing a total load of twice P, two alternators are assumed to be equally loaded. Now, if suppose the mechanical load on prime mover 1 is increased by its governor setting. For increasing the mechanical load on prime mover 1, what we have to do is to change the governor setting of the prime mover. So, supposing that governor setting of prime mover 1 is changed, and it is changed in a manner so that it is actually increasing the mechanical load on prime mover 1. Now, because of this, the speed becomes more and hence its speed load curve shifts upwards, and this upward shift in the speed load curve is represented by curve 1 dash in this particular diagram. The new operating points can very well be seen as C and D. The curve 2 will remain as it is. Curve 1 got shifted because we have increased the mechanical loading on alternator 1, on the prime mover of alternator 1. So, this caused an increment in the speed of the alternator 1. It caused the shift of the speed load characteristic of the prime mover in upward direction, and the new characteristic is being represented by line 1 dash. The new operating point would be the operating point on new curve for alternator 1 and the previous curve, because the curve of alternator 2, the operating characteristic of alternator 2 is not yet changed. So, the new operating points are seen to be C and D. Now, let us see. Let us just compare the operating condition earlier and operating condition now. Earlier, the operating points were point A and point B, and the corresponding operating frequency was the F, right? Now, when mechanical input to the prime mover of alternator 1 is increased, the characteristic curve of prime mover 1 or of alternator 1 shifted in upward direction. It is now represented by 1 dash. There is no change in the prime mover characteristic or the alternator characteristic for alternator 2. So, the new operating point would lie over curve 1 dash and curve 2. The new operating point is at point C over curve 1 dash and at point D now over the curve 2. What it is representing? It is representing that the load which is now being shared by alternator 1 is given by P1, and the load which is now shared by alternator 2 is P2. So, what we can see is load on alternator 1 is increased to P1 from the previous loading P, and load on alternator 2 is reduced to P2 from the previous load P. So, but the operating frequency is now F dash. if we need to restore the operating frequency to the frequency f, which was the operating frequency earlier, we have to do some changes in the operating characteristic of alternator 2. So, for this, what is done? A reduction in the mechanical torque of prime mover 2 causes its speed torque characteristic, speed load characteristic to shift in downward direction. So, you can see that a reduction to restore the frequency, to restore the system frequency to f hertz again, we need to reduce the mechanical input given to alternator 2. The new characteristic, the load characteristic, speed load characteristic of alternator 2 is now represented by 2 dash, and the new operating points would lie now on the characteristic 1 dash for alternator 1 and characteristic 2 dash for alternator 2. So, what we can see over here, that the new operating points are x over curve 1 dash and y over curve 2 dash. 2 dash is the new operating characteristic of alternator 2. 1 dash is the new operating characteristic of alternator 1, and what we see over here is the corresponding to the normal frequency f, the load on alternator 1 got increased to a value of P1 dash, and the load on alternator 2 is further reduced from P2 to P2 dash. Initial loading of two alternators were at P and P for alternator 1 and 2 respectively. After that, when a disturbance is created, disturbance was an increment in the mechanical loading, an increment in the mechanical input of the prime mover for alternator 1. It shifted the characteristic, operating characteristic of alternator 1 in upward direction. Corresponding load shared by the alternator 1 became P1. With this, the operating point shifted to a new frequency of f dash. The corresponding operating point on curve 2 for the alternator 2 was such that the loading of alternator 2 was reduced from P to P2. Now, to restore after this, for restoration of the operating frequency, what is done is the reduction of the mechanical input to the prime mover of alternator 2. With this reduction of the mechanical input to the prime mover of alternator 2, reduced the load shared by alternator 2 further to a value of P2 dash, and it increased the load shared by alternator 1 it increased the load shared by alternator 1 further to a value of P1 dash. Now, let us see what happens in the form of the phasor diagram, what happens internally to various voltages and currents when the mechanical input to alternator 1 is increased and mechanical input to alternator 2 is reduced. What we conclude from the previous discussion is, if we want to operate the system at constant frequency, and if for one alternator the mechanical input is increased, to restore the frequency of the system to the normal frequency, we have to reduce the mechanical input at the second alternator. The same phenomena we are going to discuss here in the form of the phasor diagram. So, here let us consider that two alternators are running in parallel with their excitations constant. What does it mean? If the excitations are kept constant, the induced EMF of two alternators in magnitude will remain same. There is no variation in the magnitude of the induced EMF when excitation is kept constant. The armature current I1 and I2 are also equal, so that the total current is twice IA1 or twice IA2. Terminal voltage VT is constant. Each alternator is sharing an equal load, and that load can be written as EF1 VT upon XS sin delta, EF2 VT upon XS sin delta, where delta is the load angle for two alternators. The two alternators are equally loaded. The terminal voltage of this parallel combination is VT, it is constant. The excitation EMF EF1 and EF2 are constant in magnitude and they are equal. Now, the two alternators are identical. Here we are assuming that the current shared, total current shared by the combination is twice IA1 or twice IA2. Here, current supplied by alternator 1 is equal to the current supplied by alternator 2, right? Now, when mechanical torque of alternator 1 is increased, its output must increase because there is an increment in the mechanical input of the alternator 1. So, there must be an increment in the electrical output of the alternator 1. But what we see over here is Xs is the synchronous reactance, it will remain constant. EF1 in magnitude will remain constant. Vt is the terminal voltage is also constant. So, actually, sine delta must increase to give an increased electrical power output by the alternator 1 as per this particular equation. So, what actually happens because of this? As I told you, EF1, Vt and Xs are constant. So, power angle must be increased from delta to some value, let it be delta 1. So, new EF will now be ahead of its previous position because there is an increment in the load angle delta for the alternator 1. Initially, the load angle was equal to delta and now it must increase beyond delta. So, the new value of this load angle is delta 1. Right? So, the alternator 1 now shares greater load than P because P was equal to this value. Now, we have got the power output as EF1 Vt upon Xs sine delta 1, where angle delta 1 is more than the previous load angle delta of the alternator. Now, let us see the same in the phasor diagram. The reference phasor is the voltage Vt, terminal voltage Vt. The current shared by two alternators, current supplied by two alternators is same, having the same phase angle phi with respect to the terminal voltage Vt. So, this is current IA1. In the same line, in the same phase, we have got current IA2 such that the total current IL is equal to twice IA1 or twice IA2. We know that current IA1 is equal to current IA2. So, this is the phasor diagram. Let me overwrite over it to show you the initial condition. Terminal voltage, this is the total current supplied to the load, and this is the position of the phasors of EMF EF1 and the EMF EF2. Agreed? This is the load angle delta for alternator 1 as well as for the alternator 2. Right? Now, let us see what happens when the loading, mechanical loading of alternator 1 is increased. As I have told you earlier that load angle changes from delta to some new increased value of delta 1. Because of this, the EMF EF1 will now be ahead of its previous position. What I have overwritten over here is the previous position. I have marked the previous position of excitation EMF EF1. Now, excitation EMF1 will now be ahead of its previous position and the new load angle is angle delta 1. This is the new position of excitation EMF EF1, right? Now, as I told you earlier in previous slides, to restore the operating frequency of the system to the same F hertz, what we have to do if we are increasing the mechanical input of one alternator, at the same time I have to reduce the mechanical input of the second alternator. What happens when the mechanical input of the second alternator is varied? The electrical output will definitely change. The electrical output of the second alternator will definitely change. The electrical output earlier was EF2 Vt upon Xs sine delta. It was equal to the initial power P supplied by alternator 2. Now what happens? Now this power should get reduced as the mechanical input to the alternator 1 got reduced. It will happen only if there is a reduction in the load angle of the second alternator. the induced EMF magnitude or excitation EMF magnitude EF will remain constant. Terminal voltage Vt is constant, axis is constant. So, the only possibility is a reduction in the term sine delta. So, there must be a reduction in the load angle delta for the second alternator. So, the new load angle for second alternator must be less than the previous value of the load angle for alternator 2. Let the new position of the alternator 2 induced EMF EF2 be this, right? So, magnitude will remain same, but the phase angle with respect to the terminal voltage Vt got reduced to delta 2. So, EMF EF1 is now at an angle of delta 1 and EMF EF2 is now at an angle of delta 2. What happens because of this? The alternator, due to the alternator 1 is having a voltage EF1, this is the new position. Alternator 2 is having the induced EMF of EF2, the new position is this. Because of different positions of EF1 and EF2, a voltage, let it be AB, appears in the local circuit of two alternators only. This potential difference in the local circuit of two alternators will cause flow of a circulating current, right? So, the circulating current would be lagging behind the voltage AB by an angle of 90 degree. Why so? Because we are neglecting the resistance part of the alternator armature circuit. We are only considering the reactance part XS. So, the circuit in which this circulating current is flowing is actually purely inductive. So, the voltage VAB or simply the phasor AB of the voltage is here. The circulating current must be lagging behind this voltage by an angle of 90 degree, right? Now, you see this circulating current will get added to the current of alternator 1 and it would be subtracted from the current of alternator 2 as the direction of current is from alternator 1 to alternator 2. If suppose this is the equivalent circuit representation, this is alternator 1, this is the reactance axis, this is alternator 2 and its corresponding reactance, this is alternator 2 and a common load is connected over here. The circulating current is flowing in this direction. So, the total current, the net current or the new current flowing in the armature circuit of alternator 1 would be the phasor sum of the component of current it was carrying earlier, that was current IA1 and the circulating current IC. So, it is in phase. This was the phasor orientation of the circulating current IC. The summation of these two actually gives us the new current carried by the alternator 1. Let this current be current IA1 dash. Now, at the same time, to get the new current of alternator 2, we have to subtract the current IC from the initial current which was carried by alternator 2. So, the new current that is now carried by alternator 2 is going to be current IA2 dash. The total load will remain same and hence the load current have to remain same. The load, we haven't changed the load connected in this system. There is no variation in this load. So, the total current carried by the load will remain constant to the value of IL. Now, the total current supplied by two alternators is the phasor sum of alternator current IA1 dash and IA2 dash, right? What else we can see over here? The operating power factor of alternator 1 is now phi 1. The operating power factor of alternator 2 is now phi 2. So, the power factor of alternator 1 got improved from cos phi to cos phi 1, whereas there is a reduction in the operating power factor of alternator 2 from cos phi to cos phi 2. But there is no variation in the load power factor. Why so? Because there is no variation in the load actually. So what we can conclude is an increase in mechanical torque in case of alternator will increase its armature current and improve its operating power factor. The alternator will share an increased load whose driving torque is increased, whereas the other alternator, which is connected in parallel, is relieved from the load, whereas the reactive power distribution remains unaffected. The reactive power distribution will remain unaffected. Why so? Because there is no variation in the excitation. Now, after studying the effect of variation in mechanical input, let us now see what happens when we vary the excitation given to the alternator, right? You see, there are two inputs given to the alternator. One is the mechanical input. Mechanical input is given to the alternator by the rotation of its rotor, right? Second input is the field excitation given to the DC field winding, which is provided over the rotor of the machine. So, the two inputs, what we are discussing over here is, if we vary any of the two inputs given to the alternator, what is the effect of this variation upon the performance, upon the operation of the alternators which are connected in parallel. So, we have already discussed the effect of variation in mechanical load. Now, let us see what happens when we vary the excitation given to the alternator. Let us consider the effect of change in excitation under two conditions. The two conditions are the no load condition and the full load condition. So, let us consider the no load case. So, considering two alternators on no load and they are working in parallel, if their excitations are adjusted properly, then the EMFs EF1 and EF2 will be equal. There will not be any current. Thus, there will not be any current in the local circuit. Now, suppose the excitation of alternator 1 is increased. I will show you the phasor diagram for same condition in the next slide. Just keep it in mind that we are going to increase the excitation of alternator 1 so that there is an increment in the induced voltage of alternator 1, and the induced voltage now becomes EF1. The induced voltage EF1 will now be more than its previous value. This will cause a resultant voltage of EC equals to, which is the voltage causing circulating current, which will cause the circulating current. Resultant voltage would be EF1 minus EF2, and it will appear in the local circuit. This can be seen in the phasor diagram. I must write EF2. EF1 will be more than that of the voltage EF2. This was a minor correction over here. The resulting voltage will definitely going to set up a synchronizing current. Let us see the phasor diagram first. This is the EMF EF1, this is the EMF EF2. EMF EF1, if the magnitude of the two is same, there will not be, this is EF1, this is EF2. If the magnitude of the two is same, there will not be any potential to cause circulating current between two parallel connected alternators, right? What we are discussing is what happens when the excitation of alter 1 is increased. So, definitely there would be an increment in the excitation voltage. The excitation voltage EF1 is now more than the excitation voltage EF2. So, because of the difference between the two, there is a voltage which will cause circulation of the circulating current in the local circuit formed by two alternators. What is the circulating current? The circulating current flows in the local circuit. Circulating current is not a part of the load current. Now, let us consider, let me show you the representation as well. It is the same representation, two alternators connected in parallel. Two alternators connected in parallel. I just wanted to show you the circulating current flowing under these conditions. They are supplying a common load. Load is constant. Current carried by the load is IL. What happens? We are considering the no load condition. So right now the load is not connected in the circuit. The load current is 0 under this condition. The only current flowing in the circuit is going to be the circulating current. This is the excitation EMF EF1. This is the excitation EMF EF2, and this is the circulating current flowing in the local circuit formed by the armature circuit of two alternators. Right now, let us consider what happens under load condition. Under load condition, when we are varying the excitation of one alternator, let us see what happens, right? So, with the help of phasor diagram, we are going to depict the same thing. For this, let me start with the initial condition. What is the initial condition? Voltage is Vt. This is the voltage Vt, and this is the excitation EMF of two alternators. The two EMFs are equal in magnitude and they are having the same angle, same load angle delta, right? Two alternators are working in parallel. If now excitation of alternator 1 is increased so that its induced EMF is EF1 is now increased to a value of EF1 dash as shown here. I'll explain the phasor diagram just after this. Now, which will try to increase the terminal voltage Vt as there is an increment in the excitation EMF of the alternator. Actually, what is the terminal voltage? It is EF1 plus EF2 divided by 2, right? If there is an increment in the excitation of alternator 1, the excitation EMF of alternator 1 will increase to the value of EF1 dash. Now, the EF1 dash, as the EMF got increased, it will try to increase the terminal voltage, but terminal voltage have to be kept constant. So, to keep the terminal voltage constant, if there is an increment in EF1 to EF1 dash, we have to reduce the excitation EMF EF2 so that there is a reduction in the a reduction. Because of this, there is the increment caused in the numerator of this equation by an increment in EF1 will get neutralized by a reduction in this, and the terminal voltage will remain constant. So, what we conclude over here is two alternators are connected in parallel. We increase the excitation of alternator 1. What happens with increment in the excitation of alternator 1? There is an increment in the induced EMF of the alternator 1. To restore the terminal voltage to a constant value, what we have to do? We have to, as per this equation, we have to reduce the EMF EF2 such that the average of EF1 and EF2 remains constant to the level of voltage Vt, right? The difference between EF1 dash and EF2 dash actually gives rise to a circulating current. See, this is the difference between the two voltages. It will give rise to a circulating current. The circulating current must lag behind the voltage by an angle of 90 degree, right? Now, let us see the load part of the phasor diagram. The alternator was supplying a total load of say I ampere. It was the summation of the currents of the two alternators. The two alternators had equal current. Total load supplied was equal to the phasor sum of the current supplied by two alternators. Now, what happens? As some circulating current is now present in this circuit, so this circulating current is flowing from the side of alternator 1 to alternator 2. Because of this circulating current, I must show you the correct direction of this voltage as well as current. This is the voltage which is responsible for the circulating current, and this is the circulating current. You consider the circulating current phasor along with the phasor of the load component of current, which was initially carried by two alternators. So, alternator 1 will now have a current IA1 dash, where IA1 dash is the phasor sum of current IA and current IC. Likewise, there is a reduction in the current supplied by alternator 2. So, alternator 2 will now be having, we need to subtract the circulating current from alternator 2 current so as to get the new value of current supplied by alternator 2. What we can see over here is, there is an increment in the alternator 1 current, there is an reduction in the alternator 2 current. You can see that the power factor angle of alternator 1 is now more. The power factor angle of alternator 2 got reduced from its previous value, but the load current is still equal to I, where I is the phasor sum of current IA1 dash and current IA2 dash, right? So, it can be seen that there is an increase in the magnitude of IA1 dash, but its active component remains unaltered. Why so? Because there is no variation in the variation in the mechanical input given to the alternator. So, the electrical output of the alternator will remain constant. Likewise, there is a reduction in the magnitude of current carried by alternator 2, but the component IA2 dash cos phi 2 will remain unaffected because it is responsible for the power output of the alternator. Likewise, there is a variation in the magnitude of EF1 dash. There is a variation in the magnitude of excitation EMF of second alternator to EF2 dash. Likewise, there is a variation in the load angle of the two alternators as well, such that EF sin delta remains constant. EF sin delta have to remain constant because there is no variation in the active power output of the alternator. So, we can say from the phasor it is clear that the alternator 1 is operated at a poor power factor. A poor power factor operation means the alternator 1 is now supplying greater reactive power as compared to alternator 2. Alternator 2 is now operating at an improved power factor. Alternator 2 is supplying a lesser amount of the reactive power. So, we can conclude that the change in excitation causes only the kVAR or the reactive power sharing of the two alternators without disturbing the kW sharing of the two machines or the real power output of the two machines. So, that's all about today's lecture. We'll continue beyond this in the next lecture. Thank you.